Okay, so I couldn't find a good video about this, so I decided to do it myself. And I'd usually do this in an in-person class, so I like how it comes out, so I figure I'll do it for you. So let me get a little pointer going here. Let's see, annotate. And so there's two learning targets, two ideas I need you to get out of this video, if you don't have them already, is what's this whole idea of local linearity and how does that relate to a function being differentiable? And then how do we show a function is continuous and differentiable at a point? Okay, and that's all deals with section 2.5, is that continuity? But then we use it in section 3 and section 3.1 and section 3.2. So one video that I posted earlier this weekend was how do you know when there's a corner or a cusp? So here's x to the third, or a vertical tangent even. So this is going to be the vertical tangent. So do you see how function's certainly continuous, right? I know that I can trace it all along, and now you know that finding the derivative is just finding the slope of a line. Do you see how as I get closer and closer to x equals 0, that becomes a vertical line. That tangent line becomes a vertical line. So this is a vertical tangent. That tells me the slope, if it's a vertical line, the derivative is, the slope is equal to an infinite slope. So the derivative doesn't exist because it's an infinite number, okay? Now, how about, so that's where it doesn't exist. And then here's a cusp, and this happens, and I made it in the other video that I made, and maybe you've seen in the text, when the numerator, when it's you're taking an odd root, is basically what this is, right? That's the cube root of x, this is the cube root of x squared. When you're taking an odd root, if the numerator is an even number, you're going to get a cusp. And you see that cusp is there, and that's what happens. And then versus a corner, well, corners happen whenever you have an absolute value in the function, and those corners are there, okay? And that's absolute. So if there's an absolute value in the function, you can be sure there's a corner. Now, I say that, and then my first learning target was talking about local linearity. So actually, let me do one other graph. Let me do x squared. Okay, and let me zoom out some here. Okay, so there's no corners, there's no cusps. And what makes it differentiable is I can zoom in. If I zoom in, right now I'm seeing a curve. But if I zoom in, and I keep zooming in, and I zoom in, if I zoom in far enough, how can I tell the difference between that curve that's x squared and this line? It looks like a line to me. So that's the whole idea of local linearity. If I zoom in far enough, I'm going to get a line. That tangent line will have a slope, and it's a line. It's a m, right? But if I go try to do something like here, let me come zoom back out. Let's look at the corner. I know you heard me say that if I have an absolute value in the equation, I'm going to have a corner. Well, here's this corner. Let's zoom in and see if I can make it be a line. See, I'm getting in pretty darn close, right? I'm within two and hundredths on either side. I don't know how close Desmo will let me get in. You see how I don't care how close I zoom in, that corner's still there. I can't get rid of it. So that's why an absolute value function, well, the plain old everyday absolute value function is not differentiable at 0 because the slope on the left is different from the slope on the right. That corner's always there. It's continuous, but it's just not differentiable. Let's zoom out and let's try that cusp function here. I wish there was a fast way to zoom out on this. Probably there is, and I just don't know what it is. Let's do that cusp. See, when I zoom in here, you can see that slope is, the slope on the left is negative, the slope on the right is positive. That cusp is still there. In fact, if I go in close enough, it's going to look like a vertical line. So what's really happened is that derivative, that slope at 0 is going infinite, right? So, and it's also on one side it's negative, one side it's positive. So I can't take the derivative of x to the 2/3 at x equals 0. How about, let's see, I'm gonna do the vertical tangent. Let's do that one. Oh, what am I seeing? Oh, here we go. I couldn't see it. Here, let's go to projector mode. Maybe that's what we need to do. Okay, so do you see, here, let's zoom out so we can see the curves. Okay, so there's the cube root of x. And as I zoom in, now in this case, I'm seeing a line. It has local linearity, but that's an infinite slope, so not differentiable. Okay, so that's that whole idea of why is a corner, cusp, and vertical tangents important. So then, so the other learning target, let's see. Let me zoom out here. Let's take a look at that paint document I had created. So I talked about local linearity and about corners and cusp and vertical tangents. Now, how do we show a function is continuous and differentiable? And there's one or two of the exercises in 3.1 and 3.2 that ask you to do this. And so, and I made one that's similar to it. Let's see, where's Desmos? Let me minimize this. Here we go. So let's turn that off. Okay, here, I'm good. Let's do this one. So here's a piecewise defined function. I'm using x squared when x is less than 1, and then I'm using this function ax plus b when it's the right of the function, when to the right of 1. So what that looks like on a problem is they're going to ask you something like this. They're going to say, okay, here's this piecewise defined function. Let me zoom in a little bit. Here's this piecewise defined function, and they want us to find m and b so the function is continuous and differentiable. Okay, so we could play around with that graph a little bit, but sometimes they're going to give you crazy functions, and will they graph? Yeah, they'll probably graph, but what you want to do is show this. So what's got to be true about in order for a function to be continuous and differentiable? Well, first off, to be continuous, the whole definition of continuity. And when I ask you this on a test, and I'm going to ask you this on a test, you're going to have to show me if that a function is continuous. Well, the limit on the left has to be the same as the limit on the right, and the limit at that value has to be the same as the function. Okay, so we'll as f of that value. I didn't write that on this piece of paper. But if I look at this, so if I look at here, let me zoom out a little bit. I got spoiled looking at the Desmos where I could just zoom out. So on the left, as I approach 1 from the left, I'm looking at this function. And when I find a limit, I just substitute in the value. So 1 squared is 1. Now the limit on the right is this expression. So again, I'm going to replace remember, I'm not equaling, I'm taking a limit. So it's all right for, even though this function is not defined for 1, I'm going to find out what happens at 1. So as I approach 1, I'm going to substitute in 1. M times 1 is m. So I have to, in order for the limit on the left to be equal to the limit on the right, I have this equation. I gotta solve m plus b equals 1. So that's one equation. And if it's just continuity we're looking for, they give you some other values that you can play with. But if I'm looking for something that's continuous and differentiable, the slope on the left has to be the same as the slope on the right. And right now, you have a license to take a limit, use one of those definitions of a derivative to find the slope. So I chose to use the limit of f of h minus f of a. So f of a plus h minus f of a all over h. And I plugged in 1 because that's what we care about, is it, right? That's what we care about is when x equals 1. So I dropped, here's my f of 1 on the left, because remember on the left I'm using the x squared function, right? So 1 plus h squared minus f of 1, which is 1 over h. And I expanded the 1 plus h, canceled out all my like terms, factored out an h, canceled out the h, brings me down to this limit expression. What's the limit of this derivative expression when h equals 0? Where I get 2. And then on the other piece, well, this is just a line, a linear function, and I know the slope is m. So that's why I didn't bother doing the limit expressions. I know what the slope is. You could, I mean, I could, but so this gives me another function. I know that since m, let's see, where did I write this? Did I write this down? Looks like I made a jump. So since the slope on the right is m, and I know the slope on the left is 2, I know that m has to equal 2. So in this equation, I dropped in 2, and then I subtract 1. So it looks like this is the function that makes it both continuous and differentiable. So now let's go back to Desmos. I hope you followed that. I mean, at this point, you've probably done enough of these that you know what I'm talking about here without going through it too fast. So that I just said what? A has to be 2 and B has to be -1. Whoop, not -2, -1. B has to be, oh, you know what I do here? Let me turn on this so we can see the whole graph. So what I did is I had Desmos not graph the left-hand side, but then I had it graph the left-hand side, left of 1, so that I can see the whole line. So what did I say? B equals, because I wanted to be able to see where B was -1. See how B is -1? So now let's turn off that dotted piece because that function is not defined there. Whoops. There we go. Now I'm going to do that local linearity trick. That looks continuous, right? And now let's do that local linearity trick. Let's zoom in and see if we can get a line. And you see, yeah, that looks like a line. So it's got local linearity, and it certainly looks like it's continuous. So that's how local linearity helps us come up and determine the slope this way, okay? Get a continuous function. I hope this was worth your time. Give me a yell if you need any help with anything.